Good morning to all. Today we will be discussing about thin film deposition. So yesterday we have discussed these things, thin film deposition. So today I am just making it a bit detailed. Uh, there are mainly two types of process are there to prepare thin films. So the one is the physical process. In that we can see evaporation by thermal evaporation or electron beam evaporation or laser or ion plating can be utilized for the evaporation of a given sample material to be deposited on the substrate. And there is another physical deposition technique which is called sputtering. Okay, in that sputtering itself, you can utilize different sources by DC source, RF oscillator source, magnetron source, and reactive sputtering also there. Okay, then there will be also physical process which is called spray pyrolysis, where we will be using flame and plasma in order to work it here. And we will be having a chemical process which is called chemical vapor deposition method. There will be thermal chemical vapor deposition is there, and MOCVD is there, and PECVD is there, that we will talk later. Okay, and in chemical process we already have seen that electroplating, electrolysis there, and sol gel method is there, and atomic layer epitaxy is there. Then finally we'll be having one more called molecular beam epitaxy. So these are the different methods to prepare thin films. Okay, so the mainly the classification is physical process and chemical process, and molecular beam epitaxy is already we said that to create the epitaxial films on a crystal substrate. Okay, so the first one, it's about vacuum evaporation. So in a vacuum evaporation, we will be heating our source material that we need to deposit on the substrate under vacuum until it evaporates or sublimates. Okay, and the evaporant is deposited on the substrate which is placed on a above or below to form the film. Okay, the physical vapor deposition process, which is a physical deposition process, and in that process you can obtain high deposition rate, and the method is simple and easy to use. And normally this will be utilized in a conductor materials in electronic circuits and devices, and dielectric and optical coatings as well. Normally the vacuum evaporation techniques will be normally used for the metals especially. Okay, especially the conductor materials like metals will be using for the deposition. Okay, so in a vacuum evaporation, so the mean free path of the atoms in the vapor should be greater than the distance from the source to the substrate. Okay, so that there will be no collision, we can ensure between the particles before it is depositing on the substrate. Okay, so the mean free path of the particle in air at temperature 25 degrees Celsius, we can say that that is 5 into 10 raised to minus 3 divided by P torr, where P torr means the P is the pressure. Okay, okay, since we have a vacuum, the pressure will be there, the pressure of the order of 10 raised to minus 6 torr. Okay, and the mean free path will be 1 by n sigma, where sigma is the area of cross section, which is pi d square we can say. Okay, and kt by p sigma, like you will be getting the equation corresponding to the mean free path. Okay, so the mean free path of the atoms in the vapor should be greater than the distance from the source to substrate is a key in evaporation techniques. Okay, as you can see that there is a key aspect when you talked about the vacuum evaporation side. Okay, now we can see in a vacuum evaporation technique the deposition rate is determined by Hertz-Knudsen equation. So that is R by centimeter square by S is equal to C into P dash by P is equal to 2 pi by mkt, where C is the evaporation coefficient and P double dash is the evaporant surface vapor pressure, and P is the hydrostatic pressure, and M is the evaporant molecular weight in that equation. K, as you can see the K equation, so it is a Boltzmann constant, and T is the temperature as you can see in this one. Okay, so the evaporation vacuum evaporation situation, the evaporation coefficient is larger for a clean surface and it will be small for a contaminated surface of the target material. And the deposition rate, which is greatly depends on the substrate to source geometry. So how do you place the substrate and the source? So that is a important value deposition rate demands. And of course, non-uniform thickness on the surface. Okay, and the uniformity of the thickness is mainly depends on two parameter. One is the distance, another one how do we the rotation of the substrate holder. If the rotation can ensure, then you can properly get a uniform film throughout the surface. So which is actually based on the Knudsen cosine law. As you can see that on a different direction and different space, the thickness will be different for a deposition rate. Okay, so in order to ensure a proper thickness, the proper rotation of the substrate holder will can do so. Okay, so there will be a non-uniform thickness on the surface due to the distance dependence, which is set by Knudsen cosine law, that is cos theta by r square. Okay, now the thermal evaporation we has been seen. What we have do here is that we will be having a coating on a wall. So we'll be placed here, you can see a crucible. So in that crucible we'll be keeping our sample material. It will be some powder. Okay, it will be a powder material. So we will be heating that material above the boiling point. Okay, uh, so that we can actually will get evaporated and the atoms will be deposited on the substrate. Okay, so we will be having a degassing from the heated connections and evaporated atom from the source will be depositing on the substrate. Okay, so when you talk about the high melting point materials can be utilized for this technique, because this should be hard to that's why we need to use metals which is having high melting point, right? So and uniformly we need to heat, and rapid change of deposition rate can occur once the reaction start. So the reaction between source and the heating container also we need to take into consideration. So that is a difficult part one have to address. This technique mostly viable for only high melting point materials. Okay, and we need to execute a uniformly heating. Okay, otherwise the deposition rate and yield will be different. Okay, so the temperature has an important role. The temperature should be steadily should be proceed for a heating purpose. So that is a thermal evaporation thing you need to focus on. Another one of evaporation technique that where we use electron beams. Okay, where we use high energy focused electron beam to heat the source material at a smaller area. You can see here we have a sample will be placed here, and we will be giving high energetic electron beams. So this will be able to deposit the sample on a substrate by heating the electron beams. Okay, so we for that electron beam production we will be using tungsten filament, so that you can ionize and give the electrons to pump to the this target material or the source material. Okay, and for a larger deposition rate one can get from this method, and the water cooled container or cavity we can use. There will be no source container reaction in this case, so the reaction source and container won't react each other in this situation. And the oscillating electron beam to heat the source material will use to get a uniform thickness films. Okay, and we can also different sources we can use in the same setup itself to get a multiple target. If you want to deposit 2-3 elements, you can also mix source materials also you can keep in this setup. Okay, so here also we need to create the vacuum inside the chamber, and further we will be heating this target material by using the electron beams and the deposited the atom that is coming out from the vapor, so which will be deposited on the substrate which is placed above. Okay, so that's how. And here you can see we placed a magnet. This magnet we placed it in order to confine the electrons that is coming from the tungsten filament to a circular path. We know that an electron in a magnetic field will be executing a circular motion. So we know that these atoms, the electrons will be confined in a circular motion. So this will be exactly whatever the electrons coming out from here, it will be directly going to the target material in a circular path to get evaporated and coated on the substrate. Okay, so that is an important aspect. And now we can see the vapor pressure with respect to the temperature, and as the temperature goes increases, the vapor pressure is actually decreasing, as you can see here. So here we have taken 1 by T as the case, and the temperature rises, the vapor pressure also increasing, that you can see over here. Okay, so it is here, it is 1 by T, and here it is temperature. Okay, and now this figure we already has been seen yesterday also, the phase diagram of gold silicon. So in a gold silicon case, you can see that the gold will be on the left side, on the silicon on the either side, and there will be a region where we will be having a gold silicon mix will be obtaining. It will be around 363 degrees Celsius we will be obtaining a gold silicon, where the mixture of silicon and gold will be having. So here you can see the melting point of silicon and the melting point of gold. Okay, and as the atomic percentage of silicon increases at 18.6, there you can see a mixed phase of gold and silicon that you can firstly see over here. Okay, so this is a kind of thermal evaporation technique that we will be using to prepare a gold silicon setup. Okay, so when you talk about vacuum evaporation, why do we use vacuum evaporation is that, so it is a low energy process, and the deposited material condense onto the substrate with the very little kinetic energy. So that is one of the advantage. And the kinetic energy, if you want to talk about the kinetic energy of the atom that is deposited on the substrate, it will be 0.5 electron volt. Okay, and in that deposition, the kinetic energy, when you talked about sputter deposition, that will be coming that will be talking on the next slides. Okay, so in a sputter deposition, the kinetic energy of particle that is coming onto the substrate, it is very high. It will be more than 10 electron volt. So it is sometimes the particle addition, the substrate addition to the substrate will be a problem. So it can, if it is possessing a kinetic energy, there is always a probability that the atoms can goes over the substrate. Okay, so it can may not be properly adhesive in that substrate also. So in that way, vacuum evaporation technique will be has an advantage since the kinetic energy is less, so that it can adhesive to the substrate very easily. Okay, now we'll talk about sputter deposition. Okay, in sputter deposition techniques, it is again a physical vapor deposition technique itself. Okay, here what we do here is that we will be taking the bombardment of and removal of the cathode material with a positive ion from a rare gas discharge. So what we do here is that we will take an argon plus ion that will be directing by applying voltage towards the cathode. Cathode means the cathode means the target source material, so the material we need to deposit. Okay, and the argon plus will be bombarded with the atoms, the source material, and the atoms will be removed and which will be deposited on the substrate which is placed above. Okay, so which is originally which is developed to deposit the refractory metals. Now the sputter deposition is able to deposit most of the material. So one of the advantages of sputter deposition is that you can do any type of material over here. You can do oxides material, you can do metal sample, you can do any other sample, you can do not polymers all, but you can do almost all the samples over here. Okay, so here you can see the sputter deposition technique where we will be having argon ion which will be for directing towards a sputtering target after ionization. Okay, so initially what we do here is that we'll be creating the vacuum inside the chamber, and we will be introducing the sputtering gas. The sputtering gas is argon here. Okay, and this argon will be ionized once you apply the chamber, and which will be directing towards the cathode, that is a sputtering target. Okay, So it will be hitting on the sputtering target and will remove the atoms from the sputtering target, and the sputtered atoms will be deposited on the substrate which is placed above here. Okay, and the film will be growth will be there. So we have seen the different stage of film growth yesterday in technique. So the main requirement for a sputter deposition is that it will be having a vacuum chamber, it will be having a pumping system, it will be having a sputtering sources and vacuum gauges and substrate holder and gas flow supply as well. Okay, so this is how here the it look like. So we need to create a vacuum in by using vacuum this chamber, and by for the pump by using pumping system and gas pumping system, and the vacuum gauges will be there too in order to monitor the pressure variation and the pressure change in the chamber. And the sputter source means it is a sputtering target. Okay, and substrate holder, so we will be holding the substrate with the holder, so that is a substrate holder. And gas flow supply, where we need to enter the gas to the chamber and to remove as well. Okay, so this gas can be sometimes an oxygen, argon will be always the sputtering gas. It can be, you can introduce oxygen, nitrogen also in as a reactive gas. So in a reactive gas means once you introduce nitrogen or oxygen, so it will be oxidizing the material inside, so you can get a nitrate or oxides by using introducing the reactive gas like oxygen or nitrogen by along with the argon. Okay, so here you can see the sputter deposition process. The ions are accelerated into the target as we have seen, and some of the surface atoms are sputtered of the target, and these sputtered atoms flow across the chamber to where they will need to deposit. That's what you can see over here. This blue color is a sputtered atom which is need to deposit on the substrate which is deposited over here. And here in that process you can will be creating a plasma. So the plasma will be containing, we know that the positive, negative and the neutral atoms will be there. Okay, and this is a simple assembly of a sputtering chamber. Will be having a cathode as a thermal sputtering target, and will be having the substrate on the top of it. Or either ഈ ഒരു അറേഞ്ച്മെന്റ് എന്ന് പറയുന്നത് വേണമെങ്കിൽ സബ്സ്ട്രേറ്റ് താഴെയും സ്പട്ടറിംഗ് ടാർജറ്റ് മേലെയായിട്ടും അറേഞ്ച് ചെയ്യാം. In either way you can see that. So the mechanism of sputtering, when you talk about the mechanism of sputtering, we can say that the sputtering involves the collision of energetic ions with the target surface, and the process usually lead to the ejection of target atoms. Okay, as you can see here, we will be having the atoms at the surface will be emitted out here, not in the volume part. So it will be and we'll be having the neutral ions, secondary electrons will be there, sputtered atoms will be there, and incident ions also will be there. So, and that's why we'll be having a plasma over there, because we are mixed ions with the neutral atoms are there. Okay, and of course there will be lattice atoms will be there. Okay, so it all depends on the energy of the incident ions, how it is kicking out the particle. Okay, so how the sputtering process is characterized is by considering the sputtering yield. So we just take it as S as the sputtering yield, which is typically in the range of 0.01 to 4, and which is increases with the mass of the material and the energy of the sputtering gas. That's what I was talking. Okay, so the sputtering yield, the whatever the content you are getting, the requirement, the gain, it will be increases with the mass of the material and the energy of the sputtering gas. Okay, so as any interaction, the ion, if it is interacting with the surface of a target material, there will be probably many interactions will be there. There will be reflected ions, neutron atoms will be there, secondary electrons will be there, and sputtered atoms will be there. So we will be as a considering that the sputtering atoms will be deposited on the substrate. The other particles which will be colliding with the different ions that is presenting in the chamber, and it will be again getting as a neutral as well. Okay, now you can see here the sputtering yield as depends on four parameters. One is the energy of the incident ion, and second one the mass of the ion and the target atom, And the third one, it is the binding energy of atom in the solid. And the D option, sorry, the fourth one, it is the incident angle of the ion. So it is incident angle of the argon ions also decided. Here you can see that for different angle the sputtering yield is varying, and here you can see with respect to the energy of the ion particle, how the sputtering yield is varying. Also you can see in this figure. Okay, the sputtering yield is very large when it comes to for the argon situation. So here if you are using argon as ion for a different target material, the sputtering yield is different for different material. You can see, so it is the sputtering yield is very high for silver target if you are using argon. Okay, that you can see over there. So here you can see the variation of sputtering yield with ion energy at a normal incidence. Okay, in this figure, and here for different incident angle the sputtering yield is varying. Okay, at a particular point up to 60 to 70 degrees Celsius you can get a better sputtering yield. That is a proper good angle for getting the sputtered atom. Okay, and sputtering alloy charges. What is the importance of sputtering? Sputtering is that it is largely you can make a number of films in a uniform manner, and it is a repeatable manner, and you can use it industrially. Very useful technique for a large scale production. You can utilize sputtering as a tool to prepare thin films. So that is a very important case. Okay, and the composition of alloy in films is approximately the same as the alloy in the target. So if you want to take a alloy target, there is a mixture of two element like cobalt iron. Okay, then if you want to deposit the alloy, then whatever that is there in the target you can get the same in the substrate also as well. Okay, and the mixing of these two alloys will be a slow diffusion mixing in solids that can happening in sputtering process, and the target, as we see, it is reached a steady state and the surface composition will be balanced the sputtering yield. Okay, because we know that when we have a combination of two materials, one is high yield material, one is a low yield material. Okay, so it will before surface equilibrium you may not be getting the proper composition, but if once the surface equilibrium is ensured, both the material will be depositing in a same fashion. Okay, so that we do in sputtering process a pre-sputtering process. Pre-sputtering means before you start deposition we will be sputtering the atom by closing the shutter. Okay, so it will be just to for initially to ensure the proper composition. Once we ensure the proper composition we can start do the sputtering further. Okay, so the main advantage of sputter deposition is that the elements alloy compound can be sputtered and deposited, and sputtering target provides a stable long-lived vaporization source. So in some configuration, reactive deposition can be easily accomplished by using reacting gaseous species that are activated in plasma, as I mentioned about oxygen, nitrogen. You can also get a metal, and by using oxide, by introducing the reactive gas as oxygen, you can get the metal oxide over there. Okay, and the source and the substrate can be spaced close together, and the sputter deposition chamber can have a small volume. Okay, and when you talk about the of course the disadvantage of a sputter deposition, the sputtering rates are low compared to that can be attained by thermal evaporation. We already said that in a thermal evaporation the high gain you can achieve, and the sputtering charges are often expensive. The material use may be poor. Okay, the target that will be, the target means it is a kind of pellet. It is a larger size of 2-inch size of pellet, like a tablet that you are using, right? So it is a larger kind of a tablet that is of 2-inch, like a that we called as target. Okay, so it is a 2-inch pellet ആണ്. So ആ 2-inch pellet often expensive ആണ്. For a pure material നമുക്ക് കിട്ടണമെങ്കിൽ it will be quite expensive, and most of the energy, so that's why I told, that's why we using in a industrial purpose normally sputtering നമ്മൾ യൂസ് ചെയ്യുക എന്നുള്ള ഇതിൽ പറഞ്ഞിട്ടുള്ളത്. Okay, most of the energy instead of the target becomes heat which must be removed, and in reactive sputter deposition the gas composition must be carefully controlled to prevent the poisoning the sputtering target. So if you introduce a gas, sometimes this gas can actually oxidize the metal if we are using a metal target. Okay, so that you cannot use the metal target next time for depositing a metals, because it would have already oxidized. So that we need to take into consideration. Okay, the in the sputtering itself, there are four kind of sputtering, we can say, depends upon the source voltage that is using. One is DC sputtering, okay, and the second one is radio frequency sputtering, where we will be using a AC current, and magnetron sputtering in order to track the electrons in a proper manner, and the reactive sputtering, here we can see the we'll be introducing a different gases over here. In a DC sputtering, it is a simplest technique. Here you can see that we'll be having anode as a substrate and cathode as a target, and we can use 1 to 2 kilovolt, okay, or you can go up to 800 volt also. Okay, 1 to 2 kilovolt you can utilize here, and you can introduce the argon gas. So the voltage that you will be applying across the cathode and across the target and the substrate will be a DC voltage here. Okay, if it is less than 2 electron voltage, there will be no ionization, elastic collision will be happen. So if you apply more than 2 electron volt, the inelastic collision will be there, and we add energy to the argon, so the ionization will be there. So it is a high energy process, like as you can see here. Okay, the energy transfer, electron gain energy via elastic collision will be there, electron greater than 15 electron volt for ionization process. So here the voltage we applied is what? So the voltage is applied is DC voltage, and the light electron will be pulled toward the faster than ion, which is leaving the slightly more than ions in a glow region. Normally this DC sputtering will be utilized in order to sputter metals, because they are more conductive, so we can easily, by applying low power, we can sputter it out here. Okay, so the operating pressure normally we need to control, so it is depends upon the argon pressure for a different sputtering yield. You can see that depends upon the optimum deposition rate around will be 100 millitorലാണ് നമുക്ക് ഒരു ഒപ്റ്റിമം രീതിയിൽ DC sputtering നമുക്ക് അച്ചീവ് ചെയ്യാൻ വേണ്ടിയിട്ട് സാധിക്കുക. Okay, and the parameter of DC sputtering is that sputter voltage will be typically 2 to 5 kilovolt ആണ്. The substrate bias voltage is being bombarded by substrate is being bombarded by electrons and ions from the target and plasma. The sputtering will be while you deposit, and we know that the neutral atoms will be deposit independently. Put negative bias on the substrate to control this, and can significantly change the different film property. And the deposition rate will change with respect to the argon pressure, and which is increases with the sputtering yield. Usually as you increases the voltage, usually the sputtering rate will increase, that you can see in that case as well. Okay, so sputtering voltage as a significant case, and if you vary the argon pressure, the sputtering gas pressure, so it can change this. Why we introducing argon there? Since argon is an inert gas, it won't react with the target material. That's why we are using argon as a sputtering gas. Okay, clear? Now we'll move on to RF sputtering. So in RF sputtering, we cannot utilize the dielectrics, insulators, semiconductors, or like rather oxides. We cannot use in DC sputtering. Okay, because the positive charge will build up on the cathode, the target material, which need at least 10 raised to 12 volt to sputter insulator. Okay, so that cannot be achieved, so it demands a lot of high power supply. So in order to avoid the charge build up by alternating potential, we use RF sputtering here. Okay, so in RF sputtering, we again the setup is same, but the voltage that is applying across the substrate and target will be a AC voltage at a frequency 13.56 megahertz. It is a standard frequency that will be utilizing in order to sputter out by utilizing RF. 13.156 megahertz എന്ന് പറയുന്ന frequency standard conventional frequency for RF sputtering in allowed ചെയ്തിട്ടുള്ളത്. Okay, and RF sputtering in the frequency less than 50 kilohertz, the electrons, ions in the plasma are mobile, and both follow the switching of the anode and cathode. Okay, so basically the DC sputtering of both surface will happen. So if you go for above 50 kilohertz കേസിലാണ് കഴിഞ്ഞാൽ അവിടെ നമുക്ക് എന്ത് ചെയ്യാം, ions cannot longer flow the switching, and which is enough to electrons to ionize gases as well. So that's why we use a 5 to 30 megahertz വരെയുള്ള റേഞ്ചിലാണ് നമ്മൾ നോർമലി എന്ത് ചെയ്യുക, അവിടെ ഇലക്ട്രോൺസിനെ അയോണൈസ് ചെയ്യാൻ വേണ്ടി ഉപയോഗിക്കുക. സോ അത് ആ റേഞ്ച് എന്ന് പറയുന്നത് നോർമലി ടിപ്പിക്കലി 13.56 മെഗാഹെർട്സ് ആണ് നോർമലി RF സ്പട്ടിങ്ങിന് യൂസ് ചെയ്യുന്ന ഫ്രീക്വൻസി എന്ന് പറയുന്നത്. So why advantage of sputtering when you talk about it is very work with insulating charges like oxides, and it has high efficiency which is easier to keep plasma going, so can operate at lower voltages and lower argon pressures and fewer gas collision, so more line of sight deposition. So these are the advantage of a RF sputtering. And now magnetron sputter deposition. So in magnetron sputter deposition, which is using along with DC and RF in DC ne kuda ubhayikkunnaanu, it has a high sputtering efficiency. How it happen? So which is increase the ionization of argon. Why? The high sputter rates at lower the argon pressures down to 0.5 milliton. So fewer gases collision will be there, and the electrons ions will be trapped by applying the magnetic field over there. So magnetron means you are applying a magnetic field across the target material, so which increases the probability of electron striking at argon, and which is increase the electron path length, and which is confining the electrons in a circular path, and which is use the electric, for that we use electric and magnetic field to confine. Here you can see that the argon ions which is accelerated to the target, which will be confined in the target material, and the surface atom will be ejected. The atoms alone will come to the sputtering target. The electrons, the primary electrons will be what? It will be trapped around the sputtering target, so that the argon ions will be again collide with the electrons. Again it will be come back to this sputtering charges. So the proper efficient ആയിട്ടുള്ള ഒരു sputtering അവിടെ സംഭവിക്കും. So it is a technology where we will be using the powerful magnets to confine the glow discharge plasma. Plasmനെ confine ചെയ്യുക എന്നുള്ളതാണ് ആ മാഗ്നറ്റ്സിന്റെ purpose എന്ന് പറയുന്നത്, which is region close to the target plane, which vastly improve the deposition rate by maintaining the high density of ion, which make the electron gas molecule collision process more efficient. Okay, so it's a process is to trap the electron around the target, and it will be confining the glow discharge. അതല്ലെങ്കിൽ എന്ത് ചെയ്യും, എല്ലാ ഡയറക്ഷനിലേക്കും അത് പ്ലാസ്മ എന്ന് പറഞ്ഞ് ചിതറി പോകുന്നതായിട്ടായിരിക്കും നമുക്ക് കാണാൻ സാധിക്കുക. അപ്പോൾ പ്ലാസ്മനെ നമുക്ക് എന്ത് ചെയ്യാൻ പറ്റും, ഒരു സർക്കുലർ ഇതിൽ പ്രോപ്പറായിട്ട് സബ്സ്ട്രേറ്റിലോട്ട് ഫോക്കസ്ഡ് ആയിട്ട് എന്ത് ചെയ്യാൻ പറ്റും, പ്ലാസ്മനെ കൺഫൈൻ ചെയ്യാനും നമുക്ക് ഈ രീതിയിലുള്ള മാഗ്നറ്റിൻ്റെ അസംബ്ലി കാരണം നമുക്ക് സാധിക്കുന്നതായിരിക്കും. Okay, so that is the advantage of magnetron sputtering: high deposition rate, reducing electron bombardment of substrate, and extending the operating vacuum range, and it is ability to operate lower pressures also. Okay, so it is the most widely commercially practiced sputtering method. It will be using along with DC and RF. DC magnetron sputtering is there, RF magnetron sputtering is there. Within one system you can also use both the power supply also. DC and RF together can come on in a single system also can be there. So it is depends upon your purpose. If you want to deposit metal, you use only DC sputtering. If you want to deposit oxide, then you can use RF sputtering. Then if you want to togetherly, if you want to sputter, you can also use both DC and RF. So they will be giving all the option when you go for a sputtering system. Okay, so for a deposition pressure, it will be in the order of 10 raised to minus 3 to 0.1 Pascal. So in terms of torque, it will be 10 raised to minus 5 to 10 raised to minus 3 torque. It is a unit of pressure. So the deposition rate will be 0.2 to 2 raised to minus 6 meter per minute ആയിരിക്കും deposition rate. Thickness of the film ആണ് പറയുന്നത്. And deposition temperature will be 100 to 150 degrees Celsius. And the disadvantage of magnetron sputtering is that the erosion track in the target material. This lead to poor efficiency of sputtering yield versus target volume compared to non-magnetron sputtering. And non-uniform removal of particle from target, which is resulting in a non-uniform films on the substrate. Okay, so this can be tackled by, as I said, by ensuring the proper rotation of the film. Okay, and now it comes to reactive sputtering. The sputtering metallic target in the presence of reactive gas with inert gases. നമ്മളിവിടെ ആർഗണിൻ്റെ കൂടെ എന്ത് ചെയ്യാണ്, ഒരു റിയാക്റ്റീവ് ഗ്യാസ് ഇൻട്രൊഡ്യൂസ് ചെയ്യുകയാണ്. അങ്ങനെയാകുമ്പോൾ എന്ത് ചെയ്യും, വി ക്യാൻ ആക്ച്വലി ഗെറ്റ് ഓക്സൈഡ്സ്, നൈട്രേറ്റ്സ്, കാർബൈഡ്സ്. ഇപ്പോൾ കാർബണോ നൈട്രജനോ ഓക്സിജനോ ഒക്കെ ഉപയോഗിച്ച് കഴിഞ്ഞാൽ നമുക്ക് ഒരു അലൂമിനിയം മെറ്റൽ ടാർജറ്റിനെ ഓക്സൈഡ് ആക്കി യൂസ് ചെയ്യാൻ വേണ്ടിയിട്ട് പറ്റും. അതുപോലെ കാർബൈഡ്സ് ആയിട്ട് നൈട്രേറ്റ്സ് ആയിട്ട് എന്ത് ചെയ്യും, നമുക്ക് കിട്ടാൻ റിയാക്റ്റീവ് സ്പട്ടറിങ് നമ്മൾ സഹായിക്കും. സോ ഇറ്റ്സ് ബേസിക്കലി അവിടെ എന്ത് ചെയ്യുന്നുണ്ട്, ഒരു കെമിക്കൽ റിയാക്ഷൻ സംഭവിക്കുന്നുണ്ട് ഓൺ എ സബ്സ്ട്രേറ്റ് ആൻഡ് ദ ടാർജറ്റ് മെറ്റീരിയൽ. സോ അതുകൊണ്ട് തന്നെ സോ ഇറ്റ് ക്യാൻ പോയിസൺ ദ ടാർജറ്റ്. സോ ദ സ്പട്ടറിങ് റേറ്റ് എന്ന് പറഞ്ഞാൽ എന്തായിരിക്കും, faster അല്ലെങ്കിൽ it will be having a reaction with the sputtering target as well. Okay, so that you should be taken care. Okay, so adjust to reactive flow to get a stoichiometry without incorporating excess gas onto the film. So this is how the reactive magnetron sputtering will work for zinc oxide film. So you can see that zinc will be having a substrate target will be here. Here will be mixed, will be introducing argon and oxygen mixture, and for to deposit getting zinc oxide. Initially we'll be having a zinc target here, so we'll be having a mixture of argon and oxygen, so in order to get a zinc oxide thin films. Okay, so the quality of the thin film depends on the deposition condition, substrate temperature, deposition power, deposition pressure, and argon oxygen flow. Okay, so those are the different parameters. One will be monitoring power, sputtering time, sputtering substrate temperature, target to substrate distance, sputtering pressure. These are the parameters one will be look after for a sputtering deposition of any material. Okay, in a conclusion, the sputter deposition is also known as physical vapor deposition or PVD. It's a widely used technique for deposition thin film layers on a semiconductor wafer. Okay, the range of application of sputtering and the variation of the basic process is extremely wide, and we know that it is probably very useful for the large production of side. Okay, and chemical vapor deposition is another technique where we told that this is a chemical process. So here we will be using a reactive carrier gas, and will we transport a precursor of a desired material to the substrate surface, and the gases will be react with the other gases and to decompose produce the stable reaction product, and which will be deposited on the substrate. The most it is a most versatile deposition technique. So wide range of chemical reactions and reactants and applications you can find for this chemical vapor deposition. So this is one of the technique in order to prepare single crystalline thin films. Single crystalline means it has only one orientation direction, and also it can be used for polycrystalline thin films, amorphous thin film, especially semiconductors of 431 category, and metals, dielectrics, superconductors, microelectronics, optoelectronics. In all these cases, CVD is widely used. Okay, so here you can see that different types of CVD is there. Thermal based CVD are there. In that APCVD, LPCVD, VLPCVD is there, and photon assisted CVD is there, laser assisted CVD is there, MOCVD is there. Okay, so this is deposited films will be there. Depends upon the stress that you are applying to the substrate. So in this process, what happen is that chemical vapor deposition, the reaction mechanism is that, so we'll be having the precursor over here, so it will be diffusing the substrate surface diffusion, and it will be deabsorbed and re-evaporated, and some of the atoms will be started the nucleation, and it will be starting the island growth in that says. So the mass transport of the reactant in the bulk and gas phase reactions will be there. Then the surface reaction will be giving rise to heterogeneous mixture of films. Okay, so which is a diffusive convective transport of depositing species to a substrate with many intermolecular collisions, which is driven by the concentration gradient of different atom. So here we take the silicon hydride will be forming by getting the main gas flow region. Okay, so initially we have a precursor as a silicon, and by using the chemical vapor deposition we will be getting silicon hydride. So we have a precursor and we have a reactor, so which is giving energy, so which we giving rise to a solid product and a gas phase products here. Okay, so the various consideration one has to taken care for a precursor is that volatility, stability, reactivity, safety, and single source precursor and common precursors. Okay, and the energy sources and reactor types also important. So depends upon, we have different type of CVDs are there. Resistive heating, quartz, tungsten, halogen lamp will be using that one, and radio frequency techniques will be the inductive heating, and laser as a thermal energy source you can use, and photon as an energy source you can use, for UV usable light will be using as a tool. Okay, so thermal activated CVD is there, where you will be using thermal energy, so which is working as a low pressure, and inorganic materials can be worked here. So it is a MOCVD, that means metal organic chemical vapor deposition, where you can metal organic compounds can be prepared, which is using a epitaxial growth will be there. So again here also we'll be using thermal and glow discharge by using UV radiations will be using here. So this is a technique of MOCVD, metal organic chemical vapor deposition. So here we'll be using a RF coil, and we'll be having a precursor over here, so substrate over here. So we will be having a mixture of elements over here. This elements will be mixing in this chamber, and the corresponding gas, the vapor that is coming out of this mixture will be collected over this substrate by applying the voltage across over here, and thus that's how you prepare the chemical vapor deposition will be working here. Another one, which is plasma enhanced CVD. Here we use plasma to ionize and dissociate gases, which is enhance the growth rate, low temperature, low pressure, and deposit SiO2 and Si3N4 films by using this technique. And there is another one, which is photo assisted CVD, which use light to enhance the reaction rate, and the effect of radiation is either a local heating of the water or a photochemical reaction. Okay, the photochemical reaction will be a photolytic reaction as well. So another one, you will be using laser assisted vapor deposition, and the atoms, the precursors will be heated up by the laser, and the vapors that is coming out will be deposited by in that method. So that is we call LCVD, laser assisted chemical vapor deposition technique. Okay, so you can see that different type of CVD: thermal CVD, metal organic CVD, plasma enhanced CVD, photo assisted CVD. Okay, and atomic layer deposition case. The thermal in inorganic sources will be used for thermal CVD, and for MOCVD again thermal energy will be using, for organometallic sources will be used as the sources to deposit. And plasma enhanced CVD, plasma which is at low temperature will be used, and photo assisted case, light will be using as a tool to induce the energy, and low temperature and selected area will be also there, and the different pressure ranges where you can obtain the evaporation that you can see for different type of CVD depositions. Okay. Okay, so the CVD deposition system will be having a rough vacuum chamber and sensors, and the source materials will be there: gas, vapor, gas carriers, gas flow control system, and the chemical reaction sources. We have a thermal heaters, plasma generating source to provide the needed energy for the chemical reaction, and we'll be having a substrate, holders, and here we know that the growth mechanism will be having a homogeneous reaction, which is at gas phase, the diffusion of the reactant to the substrate surface, and followed by the desorption of reaction byproducts from the surface, and the diffusion of products into the main gas stream as well. And on the surface there will be the adsorption of reactions will happen, okay, and possibly the heterogeneous chemical reactions will be occurs, surface migration will be there, lattice incorporation also will be there, okay. Another technique that is used in the chemical process, which is called pyrolysis, where the thermal decomposition of compound by heat and hydrates and metal carbonates organometallic compounds will be using. So it's a non-reversible process. The advantage of this spray pyrolysis or pyrolysis method is a high reaction efficiency, low temperature, less chemical attack of the substrate, and the disadvantage is that gas phase nucleation, okay. And many deposition reaction in CVD also there, and the oxidation phase substance is oxidized case, and amorphous dielectric films will be there. Hydrolysis is another method to create the amorphous and epitaxial films create another method ആണ്. So it is a different other methods ആണ്. So I'm not detailing that, okay. Other reaction in CVD, okay, that you can just look at this different setup later on. And the other one which is called ALED, so which is an atomic layer deposition, where the surface is controlled for the epitaxial growth of a single crystal. So it is originally designed for compound semiconductors. So the sequential saturated surface reactions to form a mono layer in each sequence, and which will release the exchange of ligands for saturation in each sequence, okay. So this ALD will detail once again, and will be also need to talk about molecular beam epitaxy. So that is also will talk on the next session, so that I will be keeping on the next session. So here I'll be just stopping this session on thin film deposition technique, that where we mainly talk about thermal evaporation, sputtering, then chemical vapor deposition techniques, okay. So next we need to talk about one more deposition technique. With that session will be over, that is molecular beam epitaxy, and another one atomic layer deposition technique, okay. Thank you.